Hello, today we're going to talk about Math 111. We're going to begin section 5.1. We're starting a new chapter today. Chapter 5 is entitled Exponents and Polynomials. Let me write that down. Chapter 5, Exponents and Polynomials. And in section 5.1, which begins chapter 5, we're going to start talking about exponents and rules for exponents in particular. All right, we know what exponents are and what they're all about. For example, very simply, x squared just means you've got two factors of x being multiplied. If you've got 3 to the 4th power, that's 3 factors of 3 being multiplied. 4 factors of 3 being multiplied, etc. Alright, so I'm going to assume that we know the basics of exponents and start listing these rules. Right? There's going to be about 6 or 7 rules that we cite today on how to handle exponent expressions when you multiply them, add them, subtract them, divide them, raise them to other powers, and interact other exponent expressions with other exponent expressions. It gets a little complicated sometimes. The rudiments are not too bad. Let's start out with rule 1. If we are multiplying exponent expressions with the same base, of course we know we keep the same base and add the exponents. For example, if you're multiplying y to the 11th power times y to the 5th power, we add those exponents at the exponent level and I get a final return of y to the 16th power. Alright, so let's do a couple more examples of rule 1. For example, on test day, if I ask you to simplify the following expression, we'll get, let's say, a squared times b cubed times a cubed times b. Well, of course, we know that multiplication is commutative and associative. That means I can rearrange. Let me get an eraser here. I can rearrange the order of the products here any way it suits my liking. So I can multiply the powers of a together and then multiply the powers of b together. Again, these are all implied multiplications here. And a squared times a cubed is then a to the 5th power, so those can be crunched together and simplified, times b cubed times b. Now b is one factor of b. When no exponent exists or no exponent is visible, we assume an implied exponent of 1, so b to the cube times b is of course b to the 4th power, and that would be my return for that example. Let's try another one illustrating rule 1. Let's see. Simplify the following exponent expression, minus 8a to the 4th times a squared b. Alright, and now these are all products going on here. This is an implied product, this is an implied product, this is an implied product. So again, I can crunch these powers of a together. And I get minus 8 times a to the 4th times a squared is a to the 6th power times one factor b that doesn't combine with anything else. Right? So minus 8 a to the 6th b would be the proper return there. Alright, so that's 3 examples of what we'll call rule 1. Again, the book doesn't number these rules. I number them just to keep them straight. Let's talk about rule 2. I cover them in the same order the textbook covers them, by the way. Rule 2, if I've got x to the nth power, in turn raised to the nth power. They sometimes call this a power of a power rule. And as you probably know, in a power of a power situation, you simply multiply the exponents. For example, 3 squared in turn cubed, power of a power, keep the same base, multiply the exponents at the exponent level, I end up with 3 to the 6th power, and if I multiply that out, that's 729. How about a to the 5th power raised to the 8th power? That's going to be a to the 5th times 8th power, which of course is a to the 40th power. Let's say I've got something a little more complicated. A to the 4th times a cubed inside parentheses, in turn raised to another power. Well, of course, I would want to simplify first within these parentheses before I raise to that outer exponent. All right, inside the parentheses then, that simplifies by rule 1. A to the 4th times a cubed is a to the 7th raised to the 3rd power. And now I'll use rule 2. Power of a power means I multiply the exponents. I'll call this a to the 21st power. And let's do another example of rule 2. Really right, here we go. A cubed, let's say, simplify the following exponent expression: a cubed cubed times a squared cubed. Alright, well, I can evaluate each of these exponent expressions according to rule 2 and then multiply the result according to rule 1. So I end up with a to the 9th power times a to the 6th power by multiplying those exponents. And now a to the 9th times a to the 6th is, of course, a to the 15th power. Alright, let's talk about rule 3 now. Rule 3 is really two rules in one, as stated in the book. So let me follow the author's lead here. If I've got a product raised to a power, the rule states I can distribute that exponent n, that outer exponent, over factors of that product. Similarly, if I've got a quotient raised to a power, I can distribute that exponent over the factors of that quotient. Right, so I call this rule 3 quotient to a power and product to a power rule. Let's see, if I have an example, let's give me an example of a product to a power. If I want to simplify x cubed y raised to the 3rd power, I can take each factor of that quotient and raise it to the 3rd power. All right. And then apply rule 1. I'll take this, raise it to the 3rd power, and then take this, raise that to the 3rd power, and simplify where possible. So now x squared cubed is x to the 6th power times y cubed is just y to the 3rd power. So there would be my return in this example of rule 3, product to a power. How about quotient to a power? All right, this one's going to be a little nastier. Let's see, we've got a quotient looks something like that, and I've got it, I want to raise this to the 3rd power, and I'm asked to simplify this expression. Well, what I'm going to do is work out a couple rules in one. I can see here I've got 3 factors, 3 building blocks in this product or quotient expression, and the outer exponent is 3. What I'm going to do is distribute this exponent on each piece of this product or quotient inside the parentheses individually. Alright, so minus 6 to the 3rd power. Well, let me write that down. I'm going to have minus 6 to the 3rd power. I'll figure that out in a minute. Times a to the 5th to the 3rd power. And I'll simplify that in a minute. Divided by b to the 7th raised to the 3rd power. Alright, now I can simplify this, of course, using rule 2. Minus 6 to the 3rd power, well, that's just negative 216, is it not? Similarly, a to the 5th to the 3rd power. By rule 2, I multiply the exponents, and that's a to the 15th power. And downstairs, b to the 7th to the 3rd power, I get b to the 21st power. So there is my simplified return for that kind of nasty looking example in rule 3. Alright, I want to talk about rule 4. What does rule 4 say? Rule 4 is what they call the zero exponent rule. All it says is anything to the 0 power is 1, no matter how simple, no matter how complicated. So if I ask you to evaluate 3 to the 0 power, of course we know it's 1. If I take minus 7 and raise it to the 3rd power, of course we know that's going to be positive 1. If I take 3a squared b cubed z to the 15th power and raise that to the 0 power, it will return a positive 1. Alright, now the book makes a big deal about this next example. Let's say I've got minus 5 to the 0 power. This sometimes leads to misunderstandings here, so stay awake out there. Minus 5 times x to the 0 power. I claim, according to order of operations, that the exponent gets done first, and then this negative sign outside is like a multiplier of negative 1 outside of the exponent process. So I really claim this is equivalent to minus 1 times 5 to the 0th power, and that's minus 1 times 1, which is, of course, negative 1. So beware out there, minus 5 to the 0 power isn't 1, it's negative 1 for reasons discussed previously. Okay? Alright, so that's rule 4, our negative exponent rule. I'm sorry, our zero exponent rule. Coming up next is negative exponents. Let me get a new screen here. Talk about negative exponents. The next two rules talk about negative exponents, and it could be a problem for some. There are some of us that may not have seen negative exponents before in our mathematical careers, so beware out there. Negative exponents can be troublesome. You're going to have to practice these. Basically, there's two rules involving negative exponents. I'm going to call this one Rule 5. I believe we're up to Rule 5 now. I claim that x to the minus nth power is 1 over x to the nth power. That's my rule in simplifying negative exponents. So as a simple example, if I take 3 to the minus 2, it's not 6, it's not negative 6, it's not 9, it's not negative 9. 3 to the minus 2 power, by definition, it's 1 over 3 to the positive 2 power, and of course that turns into 1/9. Similarly, if I ask you to simplify and express with positive exponents only, and you'll see this instruction occurring quite a bit on test day, etc. So I have an acronym for simplify and express with positive exponents only. Okay, that'll be our acronym for that instruction. Let's say I've got 7m to the minus 8th power. Alright, now let's think for a minute. 7 times m to the minus 8th power. That's an implied multiplication going on between 7 and m to the minus 8th power. Alright, and we know that m to the minus 8th power, by definition, is 1 over m to the positive 8th power. And if I multiply those numerators, then I just get 7 over m to the 8th power. This is my correct, most simplified answer with positive exponents only. All right, now of course in homework, tests, or quizzes, you might not want to be so formal. Basically, I take the idea this m to the minus 8th, this exponent expression, this negative exponent in the numerator will have to be shifted down to the invisible denominator of 1 and multiplied, resulting in 7 over m to the positive 8th power. Simplify and express with positive exponents only in your final answer on questions of this type. Let's keep going. How about, again, simplify and express with positive exponents only. Minus 3 to the minus 3 power. Now, we get all kinds of responses, like on test day, quiz day. Now, you just appeal to the definition. The definition of negative exponents says you got something to the negative nth power, it's 1 over something to the positive nth power. Alright, so the response here isn't 9, isn't negative 9, isn't 6, isn't negative 6. It's, well, let's see what it is. If I've got minus 3 to the minus 3 power, I claim that's 1 over minus 3 to the positive 3 power, according to my Rule 5 for negative exponents. Alright, and I can reduce that denominator, simplify the denominator now. Minus 3 to the third power, that's negative 3 times negative 3 times negative 3, and that returns a negative 27 in the denominator. So my final completely simplified answer with no negative exponents for this example is 1 over negative 27. Let's try another one similar to this. Again, this causes all kinds of trouble on test day. Minus c to the minus 1 power. Alright, just like in an example above, that negative sign outside I can rewrite as a multiplier of negative 1 times c to the minus 1 power. Now c to the minus 1 power is 1 over c to the first power, or just 1 over c. So this really reduces to minus 1 over c to the first power. Of course, more simply, minus 1 over c is my final answer for that negative exponent expression. Let's try a few more of these negative exponent examples. Simplify and express with positive exponents only. Let's say I've got x to the minus 5th power times x cubed. Well, if you're like me, you try to find the least amount of ink that you need to solve any particular problem. There's more than one way to do this problem. If I notice I'm multiplying the same bases, Rule 1 says keep the same base and add the exponents. Well, I can do that even if the exponents are negative or positive. You add the exponents, and that turns into x to the minus 2 power, and x to the minus 2 power is, of course, 1 over x squared. And you're done. Alright, here's another way. Same problem. Well, x to the minus 5th power is 1 over x to the 5th times x cubed. I end up with x to the 3rd power over x to the 5th power. Now, again, I don't know if we want to be so formal. I've got 3 factors of x. If you expand this and write it as a product of simple powers of x, I've got 3 factors of x in the numerator that will cancel out all but 2 factors of x in the denominator, and I get the same correct result, 1 over x squared, as I did by simply applying Rule 1 using a negative exponent expression. Let's try another one. Simplify and express with positive exponents only. Again, the rules are starting to layer one upon the other, and often which technique you use to solve a particular problem is often a matter of taste. Again, I like to use as little ink as possible. I've got x to the minus 3 power raised again to the minus 2 power, but I know from rule 2 that when I take a power of a power, I can multiply the exponents. And when I multiply two negative exponents, I get a positive exponent. So this is really a one-step problem if you pick the right way to go about it. Of course, there's alternate ways, but that's probably the easiest way. All right. Simplify and express with positive exponents only. Let's try this one. X to the minus 4th power over y to the minus 3 power. All right. Let me rewrite this problem down here. I'm going to need a little more room to complete this one because I'm really looking to establish a rule in general. Let's say I want to simplify and express with positive exponents only x to the minus 4th over y to the minus 3rd. Alright, I know in the numerator x to the minus 4th is 1 over x to the 4th, is it not? In the denominator, y to the minus 3rd is 1 over y to the positive 3rd power. That by definition of negative exponents. Alright, what I'm going to do here is, well, I'm taking this numerator expression and dividing it by a fraction. Of course, when we know when we divide by fractions, we can equivalently invert the divisor fraction and multiply. And of course, now if I multiply these two expressions, I get y cubed times 1, or just y cubed, over x to the 4th times 1, which is just x to the 4th. I think hopefully you can see a shortcut here. If you got negative exponents in both numerator and denominator, you can just bring in the numerator the exponent expression down and change the exponent sign, and bring the denominator expression upstairs and change the exponent sign. A little bit of a shortcut there, so you don't have to go through all these steps each time. All right. Rule 6 I want to talk about now. Rule 6 is another rule for negative exponents. So let me write this down, another negative exponent rule. I'll call this rule 6. It tells me if I've got an expression, a fractional expression with a negative exponent in the denominator, I can move this expression upstairs to the numerator and change the exponent sign. That is rule 6. All right, we can prove this to you. Let me do a little bit of a proof here for you. If I've got 1 over x to the minus n, I claim that's 1 over x to the nth power. Again, this in the denominator equals this fraction. When you're dividing 1 by a fraction, you can essentially invert the denominator fraction and multiply, and then end up with x to the nth power. So, again, let me state the rule again. 1 over x to the minus nth power is equivalent to x to the nth power. This is what I call rule 6. Okay? Alright, let's do some examples of rule 6. Let's see, 6, let's say x, let's see, hang on. Alright, what I'm going to do, erase this. Let's say I've got 1 over, let's see, give me the instructions first. simplify and express with positive exponents only. Let's start nice and easy here. 1 over t to the minus ninth power. All you got to remember, if you get a negative exponent in your denominator, you can move it up to your numerator as a factor as long as you change your exponent sign. So 1 over t to the minus ninth, by definition, is t to the ninth power. How about something like this? Five to the minus 2 power over 4 to the minus 3 power. Well, you could go the long way here and make things a little more difficult than it has to be. All you have to do is remember by Rule 1 and Rule 2, by Rule 5 and Rule 6. Rule 5 says if you've got a negative exponent in your numerator, you can bring it downstairs and change the exponent sign. So 5 to the minus 2 is really 1 over 5 squared. Similarly, 4 to the minus 3 power can come upstairs as 4 cubed. So that's probably the most concise way to grind this one out. Of course, in the numerator now, 4 cubed is 64. 4 times 4 times 4 divided by your denominator 5 squared is 25. So final return there, 64 over 25. Okay? Out of room here. Let me get another screen here. Alright. Let's say I've got a problem that looks like this. Simplify and express with positive exponents only. Alright, things like this always cause nightmares on test day, but not for us, right? Alright, we've got a negative exponent in both the numerator and the denominator, and our goal is to express with positive exponents only in our final answer. Alright, first thing I want to point out here is this negative sign in the numerator. Really, I can translate that as equivalent to being a multiplier of minus 1 in the numerator. In other words, the exponents don't see this coefficient of minus 1 in the numerator. Alright, if I note that, this turns into an easy problem now. This can go downstairs as h to the 6th power. This can come upstairs as r to the 7th power, really working out rules 5 and 6 together. So my final response is going to be minus 1 times r to the 7th power over 8 times h to the 6th power. It's really as simple as that. So don't make negative exponents or manipulating negative exponents harder than it has to be. Alright, Rule 7. I want to talk about a Rule 7 here. Rule 7 is really an extension of Rule 1. Rule 1 says when you multiply the same bases, you add the exponents. Well, you might think that, that when you divide the same base expressions, you subtract the exponents. Keep the same base and subtract the exponents. We can prove this to you very easily. If I've got a to the 5th power over a to the 3rd power, for example, and you'll see simplify perhaps on test or quiz day. Well, of course we don't have to be so formal. If I've got 5 factors of a in the numerator divided by 3 factors of a in the denominator, that means 3 factors of a in the denominator cancel out all but 2 factors of a in the denominator, right? And end up with a to the 2nd power over 1, which is just a squared, right? Of course, we could have taken a little shortcut here. A to the 5th over a cubed, according to Rule 7, is going to be a to the 5th minus 3rd power. A to the 5 minus 3 power, of course, that turns into a squared. So the same result we get the long way using Rule 7 is a little bit more concise. Let's try another one. Another example of Rule 7. Simplify and express with positive exponents only. 2x to the minus fifth over x to the 11th power. Alright, again, more than one way to complete this problem. Alright, if you want to be super formal about it, I suppose we could do it this way. 2 times x to the minus fifth minus 11th power. Again, we're here, when we're dividing the same bases, we can keep the same base and subtract the exponents. Subtract the denominator exponent from the numerator exponent, and this is 2 times x to the minus 16th power, which of course simplifies to 2 over x to the 16th power. Alright, probably an easier way to do this. You probably saw it. Same problem. I notice I've got a numerator factor with a negative exponent. I can move this downstairs as a factor by changing the exponent sign from negative to positive, and I end up with 2 over x to the 16th power in the denominator, right? So, same problem, a little bit of a different way to do it, okay? Alright. Let's try another one. Simplify and express with positive exponents only. Let's say I've got x squared over y cubed divided by 7 over x y to the 4th power. Again, we can be very formal about this, or I can say I can crunch these powers of x together. If I've got 2 factors of x in the denominator and 1 factor of x in the numerator, I'm sorry, if I've got 2 factors of x in the numerator and 1 factor of x in the denominator, well, the denominator cancels out alls but 1x in the numerator. Similarly, if I've got 3 factors of y in the denominator, in the numerator, and 4 factors of y in the denominator, that numerator will cancel out all but 1 power of y in the denominator, and of course the 7's got to remain where it is in the denominator. So my final response here, x over 7y, and I'm hoping we can do problems like this by inspection and not get too much into the formal application of the rules. Here's another one. Simplify and express with positive exponents only. And this one's kind of a nasty looking one. We're getting towards the upper limit of difficulty in this section. Alright, here we've got inside parentheses a fraction made up of factors in both numerator and denominator. What I'm going to do is simplify within parentheses before I apply this outer exponent. So let me write that down. Simplify within parentheses when you can before applying an outer exponent. Alright, so the outer exponent I'm going to leave hanging here. 2/3 doesn't reduce, so I'm going to leave 2 over 3. A to the minus 2 over a to the 5th. I claim a to the minus 2 comes downstairs as a squared, and I'll get 7 factors of a in the denominator. Similarly, b cubed over b to the 4th. If I've got 3 factors of b in the numerator and 4 factors of b in the denominator, that'll leave 1 factor of b in the denominator. Alright, I've simplified as much as I can within the parentheses now. Now I'll go ahead and distribute this outer exponent on all 4 factors that make up that quotient, product and or quotient. Alright, so 2 to the 3rd power is 8 in the numerator. Downstairs, 3 to the third power is 27 in the denominator. A to the 7th to the third power is a to the 21st power in the denominator. And of course, b to the third power in the denominator gives me 3 powers of b, or just b cubed. Oh, I don't have to put equal sign. We're done. So, depending how you look on it, this could really be looked at as a two-step problem. And not too bad once you practice these once or twice. Alright, the book talks about a Rule 8, and that's the last rule we're going to talk about here today. Rule 8, again, I number these rules, the book does not. And all this is a nice little shortcut to handle exponent expressions when you've got a fraction raised to a negative exponent. I claim if you've got a fraction raised to a negative exponent, you can invert the fraction and change that exponent sign to positive. Alright, we can prove this for you very easily, but I'll bypass the proof and just jump into some examples here. For example, 2/3 to the minus 4th power. Again, my goal is usually to express these expressions with positive exponents only. So I claim this is 3/2 to the positive 4th power, which then would just be 81/16, right? 3 to the 4th power is 81, divided by 2 to the 4th power is 16. No decimals, please. How about some variable expressions involving this rule? Nice little shortcut, really. If you can use it, simplify and express with positive exponents only. Let's say I've got a fractional expression built of variables, powers of variables raised to this outer negative exponent. Well, I can make my life a little easier. Basically invert the fraction inside the parentheses and change the exponent sign. Now I'll apply Rule 2 in conjunction with my quotient to a power rule. X cubed in the numerator, that's going to be x to the 9th power. Downstairs, y squared cubed is going to be y to the 6th power. Okay. Alright, one more example, then we'll call it a day. Let me get another screen here. Simplify and express with positive exponents only. Oh, kind of a nasty looking expression. All kinds of powers of a and b floating around inside parentheses, and to make things worse, a negative exponent outside the parentheses. Alright, what I'm going to do here is simplify within parentheses first. Almost always pays off. Simplify within parentheses first. Alright, so what I'm going to do, I'm going to leave this outer exponent hanging here. I claim, by my rule for negative exponents, I can bring a to the minus 2 downstairs as a squared, and then multiply these powers of a together in the denominator, so I'll have a to the 4th power. Okay. Now how about these powers of b? These can be simplified, crunched together too. Now you could make a big production out of this, but I think you can see these b cubes will cancel each other out, so I'll have a b to the 4th left in my denominator. And once I've canceled out everything in the numerator, there's an invisible factor of 1 that must now be explicitly written. Alright, so I've simplified very nicely inside the parentheses. Now I notice I've got a fraction raised to a negative exponent. I can invert that fraction and change my exponent sign. Well, now I've got a denominator of 1. That'll come in handy. Well, division by 1 is redundant, so I don't really need to write that. So I can just say this is a to the fourth times b to the fourth cubed. And my final response is then going to be a to the fourth cubed times b to the fourth cubed, namely a to the 12th times b to the 12th. Alright, so we reached the 40-minute point. We'll call it a day with section 5.1. Please be sure to work out all your homework problems and check your answers in the homework solutions file before you go on to the online exam. That is all.